All right, so we just obtained this solution a second ago for our application problem, and we're just going to talk a little bit about what's happening here. Because every time you have a physical problem and solve it, it's good to know that it kind of like matches up with your intuition. And we could kind of stop and think about this and look at, this is a function of time. It has an exponent of time in the denominator. Which is going to increase as time progresses. So you're going to be dividing by a bigger and bigger number. And so kind of your intuition, if you're used to taking limits, might be that at some point this is going to kind of level off. It won't go to 0 because there is this other term in the denominator. And then there's actually another way to see this, though. So we had this dh dt equal to, let's see, minus, where's our this term is what I want to be looking at. Minus h times 1,000 minus h times a minus bh. Okay. So minus h times 1,000 minus h times a minus b times h. That's what we started with. And instead of like multiplying everything through, I'm going to think about it a little bit different. I'm going to say that's minus ah times 1,000 minus h minus b times h, or minus a times h times 1,000 minus h plus, let's see, b over a. So plus b over a times minus a gives me minus b. So I just brought this inside my minus a times h. Or minus a times h times 1,000 plus b over a minus h. All of this up to this point has been algebra. But it turned it into minus r times h times k minus h. Oh, that's actually not a fraction. Where r is a and k is 1,000 plus b over a. So this is a logistic equation that we worked with way early on in class. And so a couple different things about this. First of all, now you know how to solve the logistic equation. You know that the solution to the differential equation should head to its stable equilibrium value. We've solved that like the first time we learned about critical points. So we know that we have h goes to 1,000 plus b over a. And then something else about this is we had this differential equation to start, and we rearranged it into the Bernoulli's equation form and solved it using substitution, because that's the method we know how to solve a Bernoulli equation with, and we ended up solving it as a linear equation. But we could also solve this using separation. So you have dh over h times k minus h. Sorry, I don't naturally write my h's cursive. I'm just doing it so that you don't think they're n's. It's hard to fix if I forget. Equal to minus r dt. And honestly, maybe that would have been easier. You would have to do like a fraction decomposition to take this integral right here, but it could be that you like that more than everything we did to solve it the other way. So the reason I had this little like discuss the problem video is because, first of all, I wanted to show you that the behavior of this like little infection model we wrote is the same as a logistic equation. You're going to reach the carrying capacity of the infection and just kind of get stuck there because too many people are vaccinated. So it just kind of levels out. Can't sustain any more than that. But also, there's going to be lots of different ways to solve differential equations in this class. So the way we solved it worked, but it might not have been the easiest way. We're going to do another substitution example in the next video, so go ahead and watch that whenever you're ready.